Swayam Prabha. Digital India. Educated India.
Welcome to lecture 33 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Derivation of Identification Conditions and Identification for Reduced Form. In the last lecture, we discussed the identification problem and interpretation of identification in terms of the likelihood function. We also discussed the rank and order conditions for the identification of a particular equation of the simultaneous equations model. We observed that the order condition is a necessary condition. It gives you whether a particular equation is identified or not. If it is not identified, then there is no point in going for the rank condition, which is a sufficient condition for the identification. But if using the order condition we observe a particular equation to be identified, then we must check the rank condition. We discussed a few examples where according to order condition the equation is identified, but if we check the rank condition, then we come to know that the equation is actually unidentified. In fact, the identification problem is not a sampling problem. Say you can not resolve the identification problem if you take more sample. It is a model specification problem. And before going for estimating a particular equation, we must check whether that particular equation is identifiable or not. Although we have discussed the rank and order conditions for the identification in the last lecture, in the last lecture I had not given the detailed derivation of identification conditions, which I am going to do in this lecture. In this lecture, I will also consider the identification problem in terms of the reduced form of the model. Now, before giving the derivation of rank and order conditions, let us consider one more example. We consider the Bayesian model of income determination, which has a consumption function of this form: C t equal to beta 1 plus beta 2 y t minus beta 3 t t plus u 1 t. Then it has an investment function I t equal to alpha naught plus alpha 1 y t minus 1 plus u 2 t. Taxation function t t equal to gamma naught plus gamma 1 y t plus u 3 t, and then it has an income identity y t equal to C t plus I t plus G t. Here C denotes the consumption, I is investment, T is taxes, and capital Y is income. Capital G denotes the government expenditure. Then C, I, T and Y, these are endogenous variables. G t and y t minus 1, these are the predetermined variables apart from this intercept term. Then this model has one income identity also, but identities do not raise any identification problem, because all the coefficients in the identities are known. So, you do not have to bother about the identification of income identity. Now, here capital M is equal to 4, you have 4 endogenous variables, and capital K is equal to 3. In all, you have 3 predetermined variables, including the intercept term. For consumption function, small m is equal to 3. The consumption function has 3 endogenous variables. It has C t, it has y t and t t. And then for consumption function k is equal to 1, it has just intercept term. So, k minus small k is equal to 2 and m minus 1 is equal to 2. So, according to the order condition, you have k minus small k equal to m minus 1. So, the equation is just identified if we use the order condition. Then for investment function, m is equal to 1. It has just one endogenous variable I t. K is equal to 2. It has 2 predetermined variables, intercept term and y t minus 1. So, capital K minus small k is equal to 1. 3 minus 2 equal to 1, and small m minus 1 is equal to 0. So, according to the order condition, it is over identified. For taxation function, small m is equal to 2, it has 2 endogenous variables and k is equal to 1. The 2 endogenous variables are t and y, and predetermined variable is just the intercept term. So, k minus small k is equal to 2 and m minus 1 is equal to 1. So, according to the order condition, it is over identified. Now, we check the rank condition. So, we write the coefficients in this tabular form. Then for the first equation, the matrix A is of this form. So, we obtain the matrix A by deleting the rows and columns. Say we delete this column, which is corresponding to a non-zero coefficient, then this column is corresponding to a non-zero coefficient. We delete this column and this column. Then we delete the first row. The remaining matrix is 1 0 minus 1 0 0 minus 1 minus alpha 1 0 0. So, you get this matrix. Now, we cannot form a non-zero determinant of order m minus 1 equal to 3. The only determinant of order 3 is the determinant value of A itself, which is equal to 0. You can easily verify it. Determinant of A is equal to 0. So, the consumption function is unidentified. Similarly, for the second equation, the matrix A is of this form. Now, you can easily verify it. Say, for the second equation, you obtain matrix A by deleting. So, you consider the non-zero coefficients here and delete the corresponding columns. And then you delete this row. And finally, you obtain the matrix A of this form. Now, suppose you consider this determinant, which is formed by a submatrix of order 3 by 3 of A. Now, determinant value of this matrix is 1 plus gamma 1 beta 3 minus beta 2, which is not equal to 0. So, the income function is identified. For the third equation, taxation function, now you can easily obtain A is equal to this. Again, you can get a matrix or the submatrix of order 3 by 3, which has determinant value minus 1. This determinant value is not equal to 0. So, again TF is identified. Remember, according to the order condition, the first equation is just identified, second and third are over identified. If we use the rank condition, then the first equation is unidentified. So, our final result is the first equation is unidentified. The second and third equations are identified according to the rank condition. And if we combine it with the order condition, then we observe that the second and third equations are over identified. Now, we derive the rank condition. Say we consider the model B y t plus gamma x t equal to u t, t taking values from 1 to n. Here B is of order m cross m, gamma is of order m cross k, and u t is of order m cross 1. Similarly, y t and x t are of orders m cross 1 and k cross 1 respectively. Then suppose we write z t equal to y t x t and A equal to B gamma. Then we can write equation 1 as A z t equal to u t, because A z t is equal to B y t plus gamma x t. Now, we consider the identification of first equation. So, suppose the first structural equation is alpha 1 z t equal to u 1 t, where alpha 1 is the first row of matrix A. You take the first row of matrix A, then the first equation is alpha 1 z t equal to u 1 t. Then the elements of alpha 1 have some linear restrictions, and the most common restrictions are exclusion restrictions, means some of the elements of alpha 1 are 0, or you can say some of the variables are excluded from the first equation, which are included somewhere else in your model, and those variables may be endogenous variables or exogenous variables. Now, suppose a priori restrictions are expressed as alpha 1 phi equal to 0. So, you have R restrictions, or say R elements of alpha 1 are 0, or you may have some other kinds of restrictions on the elements of alpha 1. And phi is of order m plus k cross R. So, you have restrictions of this form alpha 1 phi equal to 0. Then along with these restrictions, we have restrictions on alpha 1 arising from the relation between structural and reduced form coefficients. So, the relation between structural and reduced form coefficients is b pi plus gamma equal to 0. Actually, pi is equal to minus b inverse gamma, or you can say b pi plus gamma equal to 0, or you can write it as say b gamma pi I k equal to 0, and then we are writing b gamma equal to a and pi I k equal to w. So, you get a w equal to 0. So, we get these restrictions from the relation between structural and reduced form coefficients. So, these are the restrictions for all the coefficients, but we are mainly interested in the restrictions on alpha 1. So, restrictions on alpha 1 are alpha 1 w equal to 0. We take just the first row of A and then we take alpha 1 into, we multiply it by w and put it equal to 0. So, you have the restrictions alpha 1 w equal to 0 arising from the relations between reduced form and structural parameters for the first equation, and then you have some exclusion restrictions of this form, some restrictions on the elements of alpha 1 of this form alpha 1 phi equal to 0. Then we combine these two and we get the restriction alpha 1 w phi equal to 0. Now, how many unknowns are there in alpha 1? M plus k. It has m plus k elements. Actually, alpha 1 is a row vector and it has m elements or m coefficients corresponding to the endogenous variables and capital K coefficients corresponding to the predetermined variables. So, in all there are m plus k unknowns involved in alpha 1. Then w phi is of order m plus k cross k plus r. Number of restrictions is, you have r restrictions from the relation alpha 1 phi equal to 0, and then you have k restrictions from here alpha 1 w equal to 0. So, in fact, in equation 7 we have k plus r equations in m plus k unknowns. Then the first element of alpha 1 is 1. The first element is corresponding to, say, suppose the first endogenous variable is y 1, then the first element is corresponding to y 1, which is 1, or you can say beta 1 1 is equal to 1. So, in fact, we have k plus r equations in m plus k minus 1 unknowns. and then to determine alpha 1 uniquely, the condition is rank of W phi equal to m plus k minus 1. Then if rank of W phi is greater than m plus k minus 1, we get more than one solutions for alpha 1. That is, the equation is over identified. Now, notice that the order of W phi is m plus k plus r. Then for identification, you need the condition that rank of this matrix is greater than or equal to m plus k minus 1. So, this matrix must have number of columns greater than or equal to m plus k minus 1. That is, k plus r must be greater than or equal to m plus k minus 1. Otherwise, rank condition will not be satisfied. So, a necessary condition for rank condition to be satisfied is k plus r greater than or equal to m plus k minus 1, or r is greater than or equal to m minus 1. So, you get this necessary condition. Now, for exclusion restrictions, say suppose out of capital K exogenous variables, you have included just small k variables in your model. So, the number of coefficients set equal to 0 is capital K minus small k. So, you have capital K minus small k restrictions corresponding to the exogenous or predetermined variables, and then out of capital M endogenous variables, you have included just small m endogenous variables in the equation. So, corresponding to the endogenous variables, you have capital M minus small m restrictions, means you have set capital M minus small m coefficients equal to 0. So, the total number of restrictions is capital K minus small k plus capital M minus small m. So, the number of variables excluded from the equation should be greater than or equal to number of equations in the model less 1, that is capital K minus small k plus capital M minus small m greater than or equal to m minus 1. Because in this case capital R is equal to capital K minus small k plus capital M minus small m. So, you have this condition, or capital K minus small k is greater than or equal to small m minus 1. So, from here you get this condition. So, this is the order condition for identification, but notice that this is just a necessary condition for rank condition to satisfy. If this condition is not satisfied, then you do not have to check the rank condition. There is no point in checking the rank condition if order condition is not satisfied. Now, we prove this result. Suppose A is equal to B gamma, then rank of phi W is equal to rank of A phi plus capital K. To prove this result, we consider this model B y t plus gamma x t equal to u t. Then the relation between structural parameters and the reduced form parameters is given by B pi plus capital gamma is equal to 0, or A w equal to 0, where w is equal to pi I k. Then corresponding to the first equation, the restriction due to relation between structural and reduced form parameters is alpha 1 w equal to 0. Now, we can write A equal to B gamma, and then pi is equal to minus B inverse gamma, or you can write gamma equal to minus B pi, and then you can write B gamma equal to B minus B pi. So, this is equal to B, and then you have identity matrix here and minus pi. So, we can write A equal to B I m minus pi, and then A transpose W is equal to, say A transpose is I m minus pi transpose B transpose, and then you have W here, and we have defined W as, and then we have W equal to pi I k. So, we combine these two, and then we obtain A transpose W equal to I m pi minus pi transpose I k. Then you have B transpose 0 0 I k here. To check it, just consider A transpose first. A transpose is equal to I m into B transpose, you get this, plus pi into 0. So, you get this term, and then you have A minus pi transpose B transpose plus I k into 0. So, you get this term, and then W is equal to I m into 0 plus pi. So, you get this pi, and minus pi transpose into 0 plus I k. So, you get this I k. So, we can write A transpose W in this form. Then for any m plus k cross 1 non-null vector x, and we partition x as x 1 x 2, where x 1 is of order m cross 1 and x 2 is of order k cross 1. We have x transpose I pi minus pi transpose I k, means we take this matrix here x, this is equal to, then we write x transpose equal to x 1 transpose x 2 transpose. So, you can easily verify that you get x 1 transpose x 2 transpose, in between we have I pi minus pi transpose I, and then we have x 1 x 2, and then we multiply it. So, we get x 1 transpose x 1 plus x 2 transpose x 2, which is equal to x transpose x, and this is greater than 0. So, for any non-null vector x, we get x transpose I pi minus pi transpose I k x is greater than 0. This shows that this matrix is positive definite. So, the matrix I pi minus pi transpose I k is positive definite, and since this is positive definite, it is non-singular also. Again, if you take the determinant of this matrix B transpose 0 0 I k, which you have here, then determinant value of this matrix is equal to determinant of B, because determinant of B transpose is equal to determinant of B into determinant of I k, which is 1. Again, this is also not equal to 0, because we assume that B is a non-singular matrix. So, this matrix B transpose 0 I k is also non-singular matrix. Now, if you consider this matrix A transpose W, which is of order m plus k cross m plus k, then this matrix can be written as a product of two non-singular matrices. This matrix is non-singular, this matrix is non-singular. So, this shows that the matrix A transpose W is also non-singular. Now, we can write phi as phi equal to say A transpose W say S 1 S 2. This is a non-singular matrix. Then S 1 is of order m cross r and S 2 is of order k cross r. So, this is equal to A transpose S 1 plus W S 2. Further, A W is equal to 0. So, we have A phi equal to, we are writing phi equal to A transpose S 1 plus W S 2. Then if we take A phi, then we get A transpose S 1 here and A W is equal to 0. So, the second term vanishes. So, A phi is equal to A transpose S 1. A transpose, this is of order m cross m, and this is a positive definite matrix, and since A transpose is positive definite, it is a non-singular matrix. Say you have phi equal to A transpose S 1. And then A phi is equal to A transpose S 1. A transpose is non-singular. So, if we pre-multiply S 1 by A transpose, it does not change the rank of S 1. Now, rank of A phi is equal to rank of A transpose S 1, and since this is non-singular, this is equal to rank of S 1. Then rank of A transpose, which is same as the rank of A transpose, is capital M. Further, phi W is equal to A transpose W S 1 S 2 0 I k, because phi is equal to A transpose S 1 plus W S 2. You can write phi equal to A transpose S 1 plus W S 2, and of course, W is equal to A transpose into 0 plus you can write W into I k, and then we combine these two. So, we can write phi W equal to A transpose W S 1 S 2 0 I k. So, rank of phi W is equal to, now this is a non-singular matrix. So, rank of phi W is equal to rank of S 1 S 2 0 I k, and then rank of this matrix is equal to rank of S 1 plus rank of I k. Rank of I k is equal to k, and then we have shown that rank of S 1 is equal to rank of A phi from here plus k. So, rank of phi w is equal to rank of A phi plus k. Now, this gives you the required result. Ultimately, we have to prove this result, rank of phi w is equal to the rank of A phi plus k. So, we get this result. Now, if we make use of this result, then this result leads to the following equivalent rank condition for identification. So, an equation is identified if rank of A phi is greater than or equal to m minus 1. Say we had the rank condition, this rank of w phi greater than or equal to m plus k minus 1. Then rank of w phi is equal to, we have shown that rank of phi w or rank of w phi is equal to rank of A phi plus k. So, rank of w phi greater than or equal to m plus k minus 1 is equivalent to rank of A phi plus k greater than or equal to m plus k minus 1 or rank of A phi greater than or equal to m minus 1. So, we get the rank condition from here. Again we consider this example, say y 1 t plus beta 1 2 y 2 t plus gamma 1 1 x 1 t equal to u 1 t. Y 2 t plus beta 2 1 y 1 t plus gamma 2 2 x 2 t plus gamma 2 3 x 3 t equal to u 2 t. Then your matrix A is of the form, we collect all the, actually your A is equal to B gamma. So, we collect all the coefficients in A. So, you have 1 beta 1 2 gamma 1 1, then we write gamma 1 2 gamma 1 3 here, then you have beta 2 1 1 gamma 2 1 gamma 2 2 gamma 2 3, and then you have the restriction gamma 1 2 equal to 0, gamma 1 3 equal to 0 in the first equation. In the first equation you have these two restrictions, and in the second equation you have the restriction gamma 2 1 equal to 0. So, this is for the first equation and this is for the second equation. Now, alpha 1 is equal to 1 beta 1 2 gamma 1 1 gamma 1 2 gamma 1 3. So, we check the identifiability of first equation, and then we have the restrictions, say gamma 1 2 and gamma 1 3 equal to 0. We define the matrix capital phi equal to, say 0 0 0, you have one restriction gamma 1 2 equal to 0. So, we write 1 here, this is corresponding to gamma 1 2 and then 0. Then second restriction is gamma 1 3 equal to 0. So, we take 1 here corresponding to gamma 1 3 and then we take all the elements equal to 0. Now, suppose you take alpha 1 phi equal to 0, then you have alpha 1 equal to this. So, you get the restriction 1 beta 1 2 gamma 1 1 gamma 1 2 gamma 1 3 and your phi is 0 0 0 0 0 0 1 0 0 1, and ultimately this is equal to gamma 1 2 gamma 1 3, and then we take alpha 1 phi equal to 0. So, this leads to the restriction that gamma 1 2 equal to 0, gamma 1 3 equal to 0. Then we obtain capital A phi. A phi is equal to 0 0 gamma 2 2 gamma 2 3. And in fact, here you are getting the same matrix which you obtain by deleting the rows and columns. Say, if we delete the columns corresponding to the non-zero coefficients, means these columns, and then if we delete this row, then we get the first row we delete, then we get matrix gamma 2 2 gamma 2 3. So, we get similar kind of matrix here, and then we obtain the rank of this matrix, rank of A phi, which is equal to 1. So, what we do? First we obtain the matrix of restrictions, say capital phi corresponding to the first equation. So, that alpha 1 phi equal to 0 gives you the restrictions gamma 1 2 equal to 0, gamma 1 3 equal to 0. Then we calculate capital A phi, and then we obtain the rank of capital A phi. Now, the rank of capital A phi is equal to 1, and this is equal to m minus 1, and this shows that the equation is identified. So, we get similar kind of matrix here, and then we obtain the rank of this matrix, rank of A phi, which is equal to 1. So, what we do? First we obtain the matrix of restrictions, say capital phi corresponding to the first equation. So, that alpha 1 phi equal to 0 gives you the restrictions gamma 1 2 equal to 0, gamma 1 3 equal to 0. Then we calculate capital A phi, and then we obtain the rank of capital A phi. Now, the rank of capital A phi is equal to 1, and this is equal to m minus 1, and this shows that the equation is identified. Now, we consider the second equation, and we check the rank condition for the identifiability of the second equation. Corresponding to the second equation, alpha 2 is equal to say beta 2 1 1, gamma 2 1, gamma 2 2, gamma 2 3, and the only restriction is gamma 2 1 equal to 0. So, we define phi matrix as, because you have just one restriction. So, you have just one column in phi matrix, and then you have 0 0, and then here you have a restriction gamma 2 1 equal to 0. So, you take 1 here, then 0 0. So, if you take alpha 2 phi equal to 0, then this gives you the restriction that gamma 2 1 equal to 0. So, first we define this matrix phi, and now we obtain A phi. So, we take this matrix A and we multiply it by phi. So, A phi gives you gamma 1 1, gamma 2 1, and then we check the rank of this matrix A phi. Rank of this matrix is obviously 1, which is again equal to m minus 1. So, the equation is identified. Now, we consider the identification from reduced form. For the reduced form, the order condition is the same as that for the structural form. Say capital K minus small k greater than or equal to m minus 1. So, we check this condition for the order condition. Now, rank condition for the reduced form, we can write rank of A phi equal to, we write A equal to B, then you have I m minus pi. So, rank of A phi equal to rank of B I m minus pi phi, and then this is equal to, because B is a non-singular matrix. So, the rank of this matrix is same as the rank of I m minus pi phi. So, the rank condition is, say you have rank condition, rank of A phi is greater than or equal to m minus 1, or rank of I m minus pi phi greater than or equal to m minus 1. So, using this condition you can check the rank condition in terms of the reduced form coefficients. Then if you have just exclusive restrictions, the rank condition is an equation containing small m endogenous variables is identified if and only if it is possible to construct a non-zero determinant of order m minus 1 from the reduced form coefficients of exogenous or predetermined variables excluded from that particular equation. So, let us consider different steps for checking the rank condition. So, first we strike out the rows corresponding to endogenous variables excluded from that particular equation, which are being examined for the identifiability. Then we strike out columns referring to exogenous variables included in the structural form and then excluded from that particular equation. Then we are left with the reduced form coefficients excluded from the structural equation. And if the order of largest non-zero determinant is m minus 1, small m minus 1, the equation is identified. If it is less than m minus 1, equation is unidentified. So, let us consider this example. So, here actually we have taken the coefficients to be known, so that we can easily get the reduced form. So, your model is y 1 equal to 3 y 2 minus twice x 1 plus x 2 plus u 1. The second equation is y 2 equal to y 3 plus x 3 plus u 2, and the third equation is y 3 equal to y 1 minus y 2 minus twice x 3 plus u 3. Here y 1, y 2, y 3, these are the endogenous variables, and x 1, x 2, x 3, these are predetermined variables. So, in the first equation you are including two endogenous variables y 1, y 2 and two exogenous variables x 1 and x 2. Y 3 is excluded, x 3 is excluded from here. In the second equation y 1 is excluded, y 2, y 3 are included, then x 1, x 2 are excluded, x 3 is included. The third equation y 1, y 2, y 3, all the three endogenous variables are included, x 3 is included, x 1 and x 2 are excluded. And then we solve these three equations for y 1, y 2 and y 3. And ultimately we obtain this reduced form. Say y 1 equal to 4 x 1 minus twice x 2 plus 3 x 3 plus v 1, y 2 equal to twice x 1 minus x 2 plus x 3 plus v 2, say, and y 3 equal to twice x 1 minus x 2 plus v 3. Now, in the second equation actually small m is equal to 2, because the second equation has just two endogenous variables y1 and y2. And table of reduced form coefficients is, say we write x1, x2, x3 here, y1, y2, y3, then these are the corresponding coefficients. For the first equation, the coefficient of x1 is 4, coefficient of x2 is -2, coefficient of x3 is 3, 4 minus 2, 3. Similarly, for the second equation, you have the coefficients 2 minus 1, 1, and for the third equation, you have the coefficients 2 minus 1, 0. And first we consider the equation 1, the identifiability of equation 1. Then the excluded endogenous variable is y3. So, we delete the third row. Then included exogenous variables are x1 and x2. So, we delete first and second columns. Now, we are left with this matrix. So, we get table of pies of excluded exogenous variables and included endogenous variables, say 3, 1. Then we can form a non-zero determinant of order 1, that is small m minus 1. For the first equation, m is equal to 2. So, equation is just identified. Similarly, you can find the matrix for corresponding to the second equation. In the second equation, excluded endogenous variable is y1. So, we delete the first row. Included exogenous variables are x3, say. So, we delete the corresponding column. So, finally, you obtain this matrix. Further, for the second equation, m is equal to 2. We delete first row, we delete third column, and ultimately these are the pies. What is the maximum order of non-zero determinant which you can form? It is 1. M is 2. So, m minus 1 is 1. So, highest order non-zero determinant is of order 1. The equation is identified. And by order condition, you can verify that the equation is over identified. Then for the third equation, m is equal to 3, m minus 1 is equal to 2. In the third equation, y1, y2, y3 are included. So, m is equal to 3, m minus 1 is 2. Then again we obtain the matrix of pies of excluded exogenous and included endogenous variables, and you get this matrix. Then the highest order non-zero determinant is of order 1. You can easily verify that you cannot form a non-zero determinant of order 2 by 2 from here. Say if you take this determinant or this matrix, it has determinant 0. If you take this matrix, it has determinant 0. So, the highest order non-zero determinant is of order 1, and m is 3. So, m minus 1 is 2. So, the equation is unidentified here. So, this is how you can check the identifiability of different equations using the reduced form coefficients. So, in this lecture we have derived the rank and order conditions for the identifiability of a particular equation in a general form of simultaneous equation model. We also considered the identifiability conditions in the form of reduced form coefficients. We observe that the identifiability is a problem with the structure of the model or the specification of the model. It is not the problem of sampling. So, before going to estimate a particular equation, we must check the rank and order conditions for the identifiability of that equation. In the next lecture, we are going to discuss different methods of estimation for estimating the parameters of the simultaneous equations model. In fact, we have three types of identification conditions. Say, and either the equation is unidentified, then you do not have any option, you can't estimate the equation, or the equation is just identified or over identified. So, we will discuss the estimation procedures for just identified and over identified equations. So, I am going to stop here. Thank you.
Hello, I am Shikha Dikshit. I teach psychology and I am with the Department of Humanities and Social Sciences at IIT Kanpur. Today I am going to talk about what is health psychology. In the recent past, health psychology has emerged as one of the important areas in psychology. It is a field of study where psychological theories and concepts are applied to understand issues regarding health and illness. The two major themes which health psychologists are interested in studying are the themes of illness experience and behaviors associated with that experience. Contemporary health psychology adopts various and diverse kind of perspectives to understand health and illness issues. These perspectives include the behavioral perspective, the societal perspective and the cultural perspective. If we try to enumerate the kind of topics that health psychologists study, the range is very wide. To name a few of the topics, health psychologists study cognitions related to illness, that is health and illness related cognitions, social cognitive aspects of health and illness, cognitive adaptation, chronic illness and adaptation to chronic illness, disability, stress and management of stress. Health psychologists also study topics such as health related quality of life, social support and various kinds of coping mechanisms that people adopt to deal with illness experience. In addition to this kind of experience, health psychologists also study healthcare systems, health promotion and treatment related aspects including doctor-patient relationships. So, as we see, the range of topics is very large. Health psychologists also use qualitative methods and they study topics such as narratives of illness experience as well as social representations of health and illness. So, we see that the range of these topics is very large. However, this is not an exhaustive list. More recently, some health psychologists have adopted a critical health psychology approach. These health psychologists are, they offer a critique of mainly of the biomedical and behavioral perspective of health and illness as well as the methods and approach which is used to understand health and illness. So, critical health psychologists focus on the social, cultural and political aspects of health issues. If we look at the methodological aspects, overall health psychologists adopt quantitative methodology, they also use qualitative methodology, and many health psychologists use the mixed method approach.